So recently my colleague Chris Harrow covered geometric series in his Algebra 2 class, and that reminded me of something cool that I learned in graduate school called the Riemann Zeta function. So what is the Riemann Zeta function exactly? So by the way, this strange looking letter, that's a capital Zeta, and the function is defined as zeta of x is the infinite sum from 1 to infinity of 1 over n to the x. Now, I'm calling it x here. Typically, it's actually called z because the intention is for x to be complex. But for now, we're just going to treat it as a regular real number. And let's look at a few particular values. So if you do zeta of 1, so wherever you see an x, you plug in a 1 right here. So this is the infinite series of the integers to the power of 1. So it's 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, because here all the exponents on the integers are just 1. And this is a relatively famous series that most calculus students will be familiar with, or maybe even pre-calc students, called the Harmonic Series. And we're taught that this actually diverges to positive infinity. And there's a clever argument that sort of shows that's the case. But let's look at a different value of the Riemann zeta function. Let's look at zeta of 2. So in this case, the x would be replaced with a 2. So instead of 1 over 1, 1 over 2, 1 over 3, you got 1 over 1 squared, plus 1 over 2 squared, plus 1 over 3 squared, plus 1 over 4 squared. This is another famous series. In fact, this is the series that started the entire look at the Riemann zeta function to begin with. Before there was a Riemann zeta function, people actually looked at this series, and it was known as the Basal Problem. And it turns out it sums to pi squared over 6. And you can check this out in the calculator, and sure enough, it's getting closer and closer to this crazy number, pi squared over 6. And Euler gave a very intuitive argument about why this comes out to be pi squared over 6. It later had to be sort of cleaned up mathematically using limits and so forth, and various calculus techniques that did not exist back in Euler's time. But it turns out he was correct. So this crazy summation here is pi squared over 6. And the person that really analyzed that and cleaned up that argument was Riemann. And he sort of generalizes, this is a really interesting series. What if we looked at it in general and ended up coming up with the Riemann zeta function? So let's talk about a rather unexpected Riemann zeta value, and that's zeta of -1. So what would that mean exactly? So we plug in -1 for x here, and so you've got 1 over n to the -1 power. So 1 over n to the -1 simplifies to just be n. So this is basically saying the sum of the integers. So 1 plus 2 plus 3 plus 4 plus 5. Well, what does that come out to be? You would probably guess infinity. And that's a reasonable guess, and it turns out, no, that's actually not what it sums to. So zeta of -1 is not infinity. In fact, it's -1/12. And this is actually one of my favorite identities in all of mathematics, because it's just so surprising. It just comes out of nowhere. It's like, how could 1 plus 2 plus 3 plus 4 plus 5, going on forever, be -1/12? Well, I can't give an entirely mathematically rigorous argument. It's beyond the scope of this video, but I can give you sort of a intuitive motivation for it that Euler probably would have liked. And it's based on this idea of infinite geometric series. So just a little recap of what an infinite geometric series is. It's you have an infinite sum starting at a plus a over r plus a over r squared plus a over r cubed, and you just go on forever. And again, the thing that makes it be infinite is the fact it goes on forever. The thing that makes it be a geometric is the fact that each individual term is multiplying by r each time. And the fact it's a series just means that you're adding all these up. So it turns out, this is how you would write it mathematically. The sum as n goes from 0 to infinity of a r to the n power, a times r to the n power. And it's a pretty well-known result. Again, it can be proved rigorously that this comes out to be a over 1 minus r, provided the absolute value of r is less than 1. And this is the part I want to focus on right here. So this is something that in pre-calculus classes, or maybe Algebra 2 classes, we always emphasize to the students. And I want to actually take a step back from that for a minute, because it turns out you actually lose a lot of cool mathematics by putting this restriction on there. So what teachers often tell students is to say, well, if you didn't have this absolute value of r less than 1, you get nonsensical results. And I understand why we say that, but really it's not so much that you get nonsensical results, it's you get unexpected results. So it turns out this condition right here is actually more restrictive than it needs to be. So it actually can make sense for the ratio to not be less than 1, the absolute value of the ratio to not be less than 1. An analogy I like to use is when mathematicians first discovered I. So teachers used to tell students, oh, never take the square root of -1 because that doesn't make any sense. Well, so for centuries, people never did anything with square roots of negative numbers. But it turns out you miss out on a rich field of mathematics by just never exploring that. So actually, let's explore what happens if we actually do some play around with the infinite geometric series. So let me start off with a very basic question first. Let's do 1 divided by 3. So if you do 1 divided by 3, let's just do it with long division, see what we get. I think we all know what the answer here is going to be. So 3 doesn't go into 1. 1 is too small, so we've got to put the decimal point and extend this over. And draw a little line here. And I'm sure you guys have all seen this kind of stuff before. This is basic elementary school math. So when you do 1 divided by 3, you get 0.333. It's just going to keep on going forever in this repeating pattern. So in other words, 0.333 going on forever is just 1/3. But what are we really doing here when we say 0.333 going on forever? So there's like this infinity like swept under the carpet there. So what you're really saying is 0.3 plus 0.03 plus 0.003 plus 0.003. If you add these up, just sort of column by column, 0.300, that's the 3 here, the 3 here, the 3 here. So when you say 0.333 going on forever, what you're really talking about is this infinite series of 0.3 plus 0.03 plus 0.03. That's what 0.333 going on forever can really represent. That's what it means. So, but my claim is this is actually an infinite series because 0.3 is 3/10, 0.03 is 3/100, 0.03 is 3/1000, so that adds up to be 1/3. But this is a geometric series. So it's a geometric series where the common ratio is 1/10. You're multiplying each one by 1/10 each time, and you're starting at 3/10. So if we apply the that little shortcut formula for infinite geometric series to find the sum, it says the sum as n goes from 0 to infinity of ar to the n is just a over 1 minus r. So since the a is 3/10 and the r is 1/10, we just plug in here 3/10 divided by 9/10, that's 3/10 times 10/9. We can just cancel the 10s and get 3/9, otherwise known as 1/3, which is what we expected. But here's the part I want to focus on, and that is at no finite stage of this sum, the 3/10 plus 3/100 plus 3/1000, is the denominator ever a 3. So when we do 3/10 plus 3/100, because we're sort of adding it up term by term as we go, what do we get? Well, first we start off with 3/10, then we get 33/100, then we get 333/1000, etc., etc. So at each individual stage, the denominator is always a power of 10. But somehow, when we add up infinitely, when we add it all up, that power of 10 goes away, and it gives us something new. It gives us a 3 in the denominator, which didn't happen before. So the moral of the story is that when you go infinite, things can happen that are sort of unexpected, that didn't happen if you stopped at any finite case. So keep that example in mind, and let's look at a different series right here. Let's look at this one. So this is 1 plus a -1 plus 1 plus a -1 plus 1 plus a -1. Well, what does that add up to be? Well, there's a couple ways you could look at it. So one thing we could do is we could arrange the parentheses like so. And it turns out, by the way, I know some mathematicians are about to scowl. So what I'm about to do is sort of illegal. And I want to show you why it actually doesn't work. But pretend for a minute that like what normally works in finite math works with infinite math. And I put the parentheses here like this. So what are we going to get? Well, each of these parentheses would sum to 0. And as you will learn in calculus, sometimes an infinite number of zeros doesn't have to be what you would think. But for now, let's just go with our intuition that 0 plus 0 plus 0 plus 0 comes out to be 0. So you're like, okay, I now know what this infinite series is. I guess this infinite series is 0. However, watch what happens if we decide to do the parentheses differently. What if I group the parentheses in the series like this? Well, now what's going to happen? Well, each of these, again, is going to add up to 0. But don't forget we had this 1 in front. So now it's 1 plus 0 plus 0 plus 0, which is 1. So does this infinite series add up to be 0, or does it add up to be 1? So it seems like we get a little bit of a contradiction. It can be either way. Well, it turns out the moral of the story is that the associative property doesn't really work the way you think it does when you go to the infinite case. So it turns out this is, however, an infinite geometric series. Because going from 1 to -1, you're multiplying by -1. -1 times -1 is +1. +1 times -1 is -1. This has a constant ratio of -1. So let's actually try applying our formula here. So if we try applying our formula, the first term is 1, the ratio is -1. This is an infinite geometric series, so it sums to a over 1 minus r. If we believe this formula actually works when the ratio is -1, it turns out we get 1/2. So, and it turns out this actually is the accepted value. So it turns out 1 plus a -1 plus 1 plus a -1, when you add it up infinitely, it adds up to be 1/2. So at no finite stage do you ever get fractions. So it's like the 1/3 case, right? At any finite stage, you add it up. Okay, 1. Now I add a -1, I go down to 0. Add 1, I'm at 1 again. Oh, subtract 1, 0. Sort of flips back and forth between 0 and 1. So in Algebra 2 and Pre-Calc, we tell students, oh, this diverges because it oscillates between two values, so it doesn't really have a value. But it turns out that's misleading. It turns out it really does have, when you add it all up infinitely, it adds up to be 1/2. All right. So already that's a little bit strange enough. Let's take the strangest one step further. But before we do that, let me before we go up to one level of strangeness, let me show you another way we could have calculated this value without relying on geometric series. Let's say we don't know what this sums up to be, so we call it x. Well, let's add it to itself and see what we get. So here's 1 plus a -1 plus 1, so I'm just calling this x, and now we just add straight down. When you add straight down, there's the 1, -1 and 1 is 0, 1 and -1 is 0, -1 and 1 is 0, so this is zeros all the way down, and on this side you're getting x plus 2x. Now, here's where I'm not being terribly mathematically rigorous. How do we know this kind of infinite combination cancellation actually works? It turns out it does. The associative property doesn't work, but this actually does. Distributive property also works. So there's a few things you have to sort of take my word for, but it can actually be rigorously proved that this idea is correct. So when I add this up, I get that 2x is equal to 1. Or in other words, x is 1/2. In fact, this sort of procedure that I just used is often how Algebra 2's teachers justify the infinite geometric series shortcut formula in the first place, is they basically do this with the a's and the r's. Again, it can be more rigorously proved using limits in precalculus and calculus, but this general idea is correct. So it does turn out that 1 plus -1 plus 1 plus -1 really does sum to be 1/2. It's not a nonsensical result, it's just an unexpected result. All right, now let's get to the added level of weirdness. Let's look at this series. So let's look at 1 minus 2 plus 3 minus 4 plus 5 minus 6. We have no idea what this adds up to be, so I'm just going to call it y. And let's try the same trick that we did before that we sort of justified with the infinite geometric series here, of just adding it to itself and see what we get. So here we go. When I add straight down, so there's the 1. Notice I'm sort of shifting it over. Because I've got an infinite collection of objects, I can shift this over, and again, I'm sort of sweeping some details under the carpet here, but in general this works. So if you just add up column by column, -2 plus 1 is -1, plus 3 and -2 is 1, minus 4 plus 3 is -1, plus 5 minus 4, 1, -6 plus 5 is 1. So it just alternates 1, minus 1, 1, minus 1, minus 1, and on this side we're getting y plus y, which is 2y. But this part, the 1 plus a -1 plus 1 plus a -1, we already know what it is. We justified that with the infinite geometric series and also with this sort of algebra manipulation over here. So we know that this is actually 1/2. So we have that 1/2 equals 2y, so in other words, y is 1/4. So now we know remember what y was. Y was this infinite series that we didn't know what it was. Now I want to point out this actual series is not geometric. We're using geometric series to sort of justify the manipulations for what we're going to get for the sum, but by itself it's not geometric. So, but we have now justified that 1 minus 2 plus 3 minus 4 is actually 1/4. And now I'm going to use this to finally justify the sum of the integers. So I started off with the 1 minus 1 plus 1 minus 1. From that, we figured out what the alternating series of integers is, but let's get the full Monty. So let's take a look at 1 plus 2 plus 3 plus 4. No more minuses. Just do the general sum. Again, at any finite stage, it quote-unquote diverges, right? You get 1 plus 2, which is 3, plus another 3 is 6, plus another 4 is 10. It's just getting bigger and bigger and bigger. So it seems like the answer would be plus infinity, but it turns out it's not. So let's just call it Z, or Z, sorry, I say it the American way. So let's call this Z and see what we can do with this. So let's subtract from this the series we just had a second ago. So we're going to subtract 1 minus 2 plus 3 minus 4 plus 5 minus 6, and we already know what that comes out to be. We know that comes out to be negative 1/4 from what we did on the previous page. And let's just do our adding straight down trick, or in this case subtracting straight down. So we get 1 minus 1 is 0, 2 minus a negative 2 becomes a plus 4, 3 minus 3, 0, 4 minus a negative 4 is plus 8, and it kind of keeps on going in this pattern just to make sure we get the idea of what the next one's going to be. So after the plus 5 would be a plus 6, and here after the plus 5 would be a minus 6 because the second line in green is the alternating integers. So, and now we get 6 minus a minus 6, which would be plus 12. And on this side, we're just, when we add straight down, we're getting Z, or Z, since we don't know what that is yet, minus a 4th. Well, let's look at this. We have 0 plus 4 plus 0 plus 8 plus 0 plus 12. Well, let's go with our intuitive notions that the zeros sort of don't really matter. And again, the distributive property does hold with infinite series like this. And again, you should probably question that. It's like, well, how do we know that's really true? I'm not proving that in this video, but it turns out it can be rigorously justified. That this right here, it matches our intuition. This is actually 4 times 1 plus 2 plus 3 plus so on, right? Because 4 times 1 is 4, 4 times 2 is 8, 4 times 3 is 12. It turns out this actually works to give you Z minus a 4th. But this thing in parentheses is what we called Z. This is what we're trying to figure out. The 1 plus 2 plus 3, that's the Z. So what we really have is 4 times Z equals Z minus a 4th. And now we can just use our pre-algebra skills and solve for Z. So we just move the Z over, so you get 3Z equals negative 4th. So Z, after you divide by 3, is negative 12th. But what was Z? Z was what we were trying to figure out here. Z is the 1 plus 2 plus 3 plus 4. So we now know that is negative 12th. And that is sort of a general idea of why the Riemann Zeta function of negative 1 evaluates to be negative 12th. So again, I think one of the most surprising formulas in math is that when you sum the integers, 1 plus 2 plus 3 plus 4, you get negative 12th.